Hello world, I'm Sana from Router Protocols Development team. In today's tutorial, we are going to discuss one of the key features of Router Protocol, cross-chain meta-transaction. Let us first understand what a meta-transaction is. Meta-transaction is a type of transaction that allow users to sign the transaction without having to pay the gas fee associated with it. We know that every blockchain transaction requires some fee to be paid in order to execute the transaction. Meta-transaction allow developers to offload the cost of the transaction to a third-party contract or the application itself. Meta-transaction usually occurs in a single-chain environment, while cross-chain meta-transaction occur in routers cross-chain environment. Meta-transaction does not require source gas fee payment, while cross-chain meta-transaction requires source gas fee payment from the user. Meta-transaction paves gasless transaction of the same chain world, while cross-chain meta-transaction allow gasless transaction of interoperable world. In meta-transactions, decentralized applications partner with the gasless transaction service provider and settle the bill in fiat currency. In cross-chain meta-transaction, root token is used for settling gas on bridge layer and the destination chain. It uses prepaid fee pay model. That means developers of the application needs to load funds in fee pay address, and that will be used to pay for the gas on various transactions. With the help of router protocol, users can initiate transaction on one blockchain network and have them executed on another network, building for a truly interoperable world. The structure of gas payment and cross-chain transaction is different from single-chain transaction. In single-chain environment like Ethereum, all you have to pay is the Ether gas fee and the transaction is executed. However, in the case of cross-chain transaction, there are broadly three kinds of fee involved. One is the gas fee you pay on the source blockchain. Next is the bridge fee you pay on the bridge or the interoperability layer. In our case, it is the root token. Finally, the destination gas fee required to do the transaction on the destination chain. When a DApp initiates a cross-chain request, the associated fee is paid by the DApp's corresponding fee pair account on the router chain. That is called the fee pair address. This account can be set and changed by the DApp for all the integrated chain and can be changed at any time. To set the fee pair, you can use the set DApp metadata function on the chain's gateway contract. This function takes a valid router chain address as an argument. The IDApp owner can also use this function to change the fee pair address from the source chain. Meta transaction can detect fee from user's address or another wallet with their approval, allowing flexibility and streamlined collaboration in complex transactions. Once you set the fee pair, they will be able to pay the fee for your DApp's cross-chain request. The fee will be automatically detected from the fee pair account after their approval. To prevent unauthorized usage, the designated fee pair address must perform the fee pair approval transaction on the router chain. To approve the fee pair, access the router explorer and find the DApp or the fee pair address. Connect the fee pair wallet and approve the pending request. That we will see in the coming session. After the fee detection, if the destination chain is a third party, Relay will pick up the signed transaction from the orchestrator and forward it to the router's gateway contract on the destination chain. Or if the destination chain is the router chain itself, the request is sent to the designated contract on the router chain. Now, let's see how the gas price are set and how the fees are calculated. We know that gas price at gas limit plays a crucial role in determining the transaction cost. The gas price for inbound transaction on the router chain are set through governance and included in the chain's configuration. Developers need to configure a gas limit parameter in the request metadata, which is then multiplied by the gas price from router chain configuration to calculate the amount of root token to be detected from the specified fee pair address. If the gas price is set to 0, the gas price oracle on the router chain will estimate the correct value. If you are running your own relayers, you can pass a gas limit of 0 as the relayer will automatically calculate the correct gas limit for the transaction. The bridge contract automatically sets the gas price and the gas limit for outgoing cross-chain requests to cover the transaction cost on the destination chain. The router chain uses oracles to convert the gas cost from the destination chain's native token to the road token. This makes cross-chain transaction easier because the destination gas is also paid in root token, which means the fee payer does not need to bother the different destination gas token. While using crosstalk uses a prepaid fee pay model, which means when you send a crosstalk request, the router chain will estimate the fee for executing the transaction on the destination chain and detect the fee plus an incentive from your account upfront. To enhance the security and prevent Sybil attacks, the router's gateway contract charge a minimal fee from the application contract on the source chain for the orchestrator validation. This fee, paid in the source chain native token, adds an extra layer of protection. To maintain a secure payment system, all fees and relayer incentives for the cross-chain request on router can only be paid in root token. Once router chain receives the acknowledgement from the destination chain's gateway contract, it pays the fee used along with the relayer incentive to the relayer from the already deducted fee and refunds the surplus fee back to the fee payer address. This mechanism ensures that relayer receives their incentive automatically without any delay, and application can send extra gas limit as buffer since they will get automatic refunds in the case of surplus fee. Now let's move on to the live coding session to build a simple smart contract using router crosstalk. In this session, we will create a cross-chain message transfer contract that will transfer messages between different chains, and we will use cross-chain meta transaction for fee payment. We are going to use Remix IDE for deployment. Let's create a new file called sample.sol. First of all, we will import the necessary libraries and define our contract. The router EVM gateway contract is the key to connect EVM compatible chains with the router chain. We can deploy this gateway contract on any EVM compatible chain which is supported by router. Next is to set variables and constructor. We will have an owner address, the address of the gateway contract, and a variable to store messages. We will create a constructor with a gateway address and the fee pair address in the string format and set these variables inside the constructor. Now comes the cross-chain meta transaction part. We will set the fee pair address on the router chain using setDApp metadata function. Note that this is essential for facilitating cross-chain transactions available in the gateway contract, and it allows you to set the fee pair address, which is the account that will take on the responsibility of covering the transaction fees, that is the bridge fee and the destination gas fee. Once the fee pair address is set, this account must give their one-time approval to act as the fee pair for the contract on the router chain. Note that without the approval, your DApp won't be able to execute any cross-chain transaction. There is also a refund mechanism in place. Any fee refunds resulting from these transactions will be credited back to your DApp's fee payer address on the router chain. For example, if the estimate is the transaction will take 5 road tokens, but it actually just takes 4 road tokens. This can happen because the system is very dynamic. Then, one road token will be refunded to this fee payer. Now, we are writing and implementing the ISIN function in router gateway contract. This function will facilitate the transmission of cross-chain message passing based on the requirements from the source chain to the destination chain. Some of the parameters that can be configured while calling this function are destination chain ID, destination contract address, message, and the request metadata, which is a byte encoded string which includes various parameters crucial for the cross-chain interactions. Let's take a closer look at the parameters that included in the request metadata. Destination gas limit, destination gas price, acknowledgement gas price, relay of fees, acknowledgement type, is read goal, and ASM address. To achieve this functionality in your contract, you can add a get request metadata function. Developers can efficiently package the request metadata with the required parameters. This avoids the need for on-chain encoding and simplifies the cross-chain communication. Now, to complete the cross-chain communication process, we need to include an iReceive function in the destination chain contract that will be responsible for handling and processing incoming cross-chain requests. This function receives the payload initiated from the source chain along with some information such as address of the contract that initiated the request, the payload itself, and the source chain ID. With this information, one can process the payload and complete the cross-chain transaction. In the programming demo, we are going to deploy barebone smart contract on both the Polygon Mumbai network and Avalanche Fuji network using Remixide. And then we are going to send a transaction from Mumbai network to the Fuji contract by leveraging the cross-chain meta transaction. You can use chainless.org to set the network in your wallet. So let's set the network. First, we will compile our contract using the Solidity compiler. Once it's all set, head to the Deploy and Run Transaction tab. Choose Injected Provider MetaMask as our environment and connect your MetaMask to the Polygon Mumbai network. So, in order to deploy a contract on Polygon Mumbai, make sure you have enough Matic token or else can get it from the faucet. Now we need to pass constructor arguments such as fee pair address and gateway address for the Polygon Mumbai network. So the gateway address of respective chains are listed over here. Copy the gateway address of Polygon Mumbai network with the chain ID 8001 and paste it over here. And we need some root tokens to act as a fee pair. So let's go to the faucet of router and add the router network by connecting the MetaMask. Now the network is added to our wallet. Now we have enough root tokens to act as a fee pair. So I'm copying my wallet address and paste it over here. And transact. Confirm the transaction. Now let's compile and deploy it on Avalanche Fuji network. So first we need to change the network from the MetaMask and connect to the Avalanche Fuji testnet. Now let's get some AVAX token. Copy the gateway address of Avalanche Fuji network and paste it over here and deploy. Confirm the transaction. Now the contract has been deployed in Polygon Mumbai network as well as Avalanche Fuji network. So switch to the Mumbai network and let's interact with the contract. Go to the get request metadata function and pass the values. The destination gas limit and source chain gas limit can be calculated using tools like Hardhat Gas Reporter. Also, the gas price of the source chain and destination chain can be calculated using RPC of respective chain, and to avoid the need for calculation, it can be passed as 0. The router chain will then estimate the real-time gas price for them. So I am passing destination gas limit as 3M, destination gas price as 0, and acknowledgement gas price as 2M and acknowledgement gas price as 0. Next is the relayer fee. It is the fee for relayers handling cross-chain request. It is similar to the priority fee on other blockchain network. It is used to incentivize the relayers to prioritize your cross-chain request. The higher the relayer fee, the more likely your request is to be processed quickly. If you set the relayer fee to 0, the router chain will default take the minimum fee value, and this value is determined by the router chain's consensus mechanism. So let's pass it as 0. Next is the acknowledgement type. It specifies whether or not you want an acknowledgement back to the source chain after the contract calls have been executed on the destination chain. You can choose from 4 options. 0 if you don't want the acknowledgement to be forwarded back to the source chain. You can pass 1 if you want to receive the acknowledgement if the calls are executed successfully on the destination chain. And we can pass 2 if we want to get an acknowledgement back to the source chain if the calls errored on the destination chain. And pass 3 if you want on both cases, that means success or error. So I am setting it as 0 now. Next is the isRead call. It is the Boolean flag indicating whether the request is a read call. isRead call specifies whether you want to query a contract from another chain and get the data back to the source chain through the acknowledgement. If you just want to query a contract on the destination chain, set this to true. For example, if you set acknowledgement type to 1 and isRead call to true, you will only receive an acknowledgement back to the source chain if the contract calls executed successfully on the destination chain. And you will also get the data back from the query. Here I am setting it as false. Next is the ASM address. We also provide a modular security framework for creating an additional layer of security on top of the security provided by router chain. This will be in the form of smart contracts on the destination chain. The address of this contract needs to be passed in the form of a string in this variable. I am just passing as X. Now all the values are set. Click on to the call button. So it will generate a metadata. Just copy the metadata so we can use it in the isend function. Go to the isend function and type the destination chain ID. Our destination chain is Avalanche Fuji testnet and its chain ID is 43113. And copy the contract address of your Avalanche Fuji contract and paste it over here. And pass the message you wanted to pass to the Avalanche Fuji contract and copy the request metadata that generated from get request metadata function and paste it over here. Click on transact button. Confirm the transaction from the wallet. Now visit Router Explorer for testnet and connect your wallet by clicking on Connect Wallet button. Select your wallet and click on Switch Network to switch to the router testnet. Approve the pending transaction by clicking on Approve button. Sign the transaction from your wallet. Yes, now the transaction has completed. Let's go to the cross-chain tab of the Router Explorer to see our transaction over there. Click onto our transaction. This is our transaction. We can see the timeline has completed. Also, the fee details are over here. And let's see if the message is received by the Avalanche Fuji contract. So that first switch to the Avalanche Fuji network and go to the contract instance of the Avalanche Fuji contract and click on to the message button. Here we can see the hello router message we sent from the Polygon Mumbai network. I hope you enjoyed this tutorial on cross-chain meta transaction. See you in the next video.